Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I see we have all kinds of questions saved up or arriving from our form on the web. Let's see, I see one here from Cade. How does an Easter bunny lay eggs? I think that one is challenging. I think that the myths that led to the eggs are different from the myths that led to the Easter bunny, but probably sometime in history they merged. I mean, it's always a little bit, from nursery rhymes on, it's always a little bit terrible if you try and decode what these nursery rhymes actually mean. They're often things that were quite, they're not as even necessarily as G-rated as one might think back in the past. I certainly remember, well, there's things like, the Humpty Dumpty sat on a wall. That one is not too bad, but that one, I'm pretty sure was what is it? All the king's horses and all the king's men couldn't put Humpty back together again. I believe the original Humpty Dumpty was some kind of siege machine that was used in the English Civil War in the 1600s. And when the Humpty Dumpty was pushed off the wall of the city it was trying to scale, as the nursery rhyme says, all the king's horses and all the king's men couldn't put Humpty together again. Of course, it's probably the case that there are three other origin stories for that nursery rhyme, and it's serious work to try and figure out what's correct. I know another one that, again, I'm not always certain which ones exist in different places around the world, but at least in England, and I don't think I've learnt these things since I was a kid, and I guess my kids weren't big enthusiasts of some of these, so I didn't learn from them. But the Ring a Roses, Pocket Full of Posies, etc., etc., etc. That one has terrible origins in the Black Death, bubonic plague in England in the 1660s, I think, and it's kind of a prescription for, in a sense, how not to get sick and what happens if you do get sick, type thing. So these things, these traditions have a habit of having origins in history, and then they get quite distorted. So I don't know the full Easter bunny story. I think that the whole Easter story is always kind of interesting from a science point of view, because there are some holidays like Christmas Day, for example, December 25th. Okay, in the standard kind of Western Christian tradition, it's December 25th is Christmas Day. I think in other, if I'm not mistaken, in like Greek Orthodox, Russian Orthodox traditions, I think it winds up being like in January, maybe January 7th or something, but it's always on a fixed day of the year. Easter, on the other hand, switches around which day of the year it's on, because Easter has a much more complicated method for computing when it should be, because it's based on the lunar calendar rather than the solar calendar. When the days of the year, as we name them from January 1st to December 31st, are ultimately based on thinking about how the sun, how the Earth orbits around the sun, and at what point the Earth will come back to the same place it was before. After 1 year, it's always a little bit tricky whether it's a tropical year or other kinds of years. After 1 year, one says the Earth has come back to the same place that it was before in its orbit around the sun. And that the time it takes for the Earth to come back to the same place isn't a whole number of days. It's not 365, it's 365.1, I think. So it's roughly 365 and a quarter, which is what leads to our leap year convention, because instead of saying there's a quarter of a day per year, which would be very inconvenient, because then we'd end up with sort of a time zone shift for our days. Instead of doing that, we kind of fix it up every 4 years by saying there's a leap year. But that isn't quite right because it's not exactly 365 and a quarter. It's a little bit off that. And so then there has to be this extra convention that was introduced in the 1500s of having a missing leap year every 100 years, and then an extra one every 400 years, and so on, to kind of keep the rotation of the Earth aligned with this calculation of when the Earth will be back to the same place in its orbit around the sun. But when it comes to Easter, it's based on lunar calendar. That is, it depends on how many times the moon has gone around the Earth. Moon goes around the Earth roughly 13 times in a year. That leads to a lunar month of roughly 28 days, I guess. But it's not exactly that. And it's a complicated piece of calculation to figure out when the moon is going to be in a certain position. And actually, the calculation of the date of Easter was one of the early kind of difficult mathematical calculations that was being done in the 500 years ago or more. So it's a tricky thing to work that out. And it's in different traditions around the world. There's sort of a mixture of lunar, solar, etc. calendars particularly for holidays and so on. So it gets to be a kind of complicated thing. Anyway, I don't think that explains anything about the Easter bunny and its eggs, but perhaps interesting anyway. All right, let's see. Another question we have here from memes. Question is, what is the Planck temperature, the limit of potential heat? And how does it relate to the limit of potential heat? All right, let's see. That's a kind of a physics question. So let's dive into that a little bit. So first of all, what is temperature? So temperature is the energy with which molecules, for example, in a gas or any other material are the energy that the molecules, the average energy that the molecules in a gas have. So when you heat things up, what it means is you're putting energy into the material, and that means that the particles that make up the material are running around more and more quickly. They have higher and higher kinetic energy of motion. So and so what happens is that the standard thing we see with typical materials is that we go from the molecules are not running around very quickly, and they're all getting stuck together, and the thing is a solid. The molecules are running around more quickly, it becomes a liquid. Eventually, the molecules are running around so quickly that the forces of attraction between them are not enough to kind of pull them together into a blob of stuff like a liquid, and they just become a gas. Okay, so what you might think is, okay, you can keep going and just heat the thing up, just keep heating it up forever and ever and ever. And so what goes wrong if you start making things hotter and hotter? So for example, I don't know, the temperature of the center of the sun is perhaps 10 million degrees centigrade. That's pretty hot. That's also the kind of temperatures one needs if one is trying to make fusion, is one's trying to get hydrogen atoms to fuse together to make energy, either in a fusion reactor or in a hydrogen bomb. One needs millions of degrees centigrade of energy. And what happens at millions of degrees centigrade is that the hydrogen atoms are going so quickly that the fact that the hydrogen atoms, the nuclei of hydrogen atoms, normally repel each other electrically, you overcome that force of repulsion by the things just ramming together with enough speed that they can then merge and produce a lot of energy when they fuse. So the question is, when you heat things up, how hot can you make things? Well, all kinds of things might happen when you make things very hot. So one of the issues is if you make, let's see how to explain this. A couple of different things. So when you have a lot of heat, that means there's a lot of energy somewhere. So some little piece of gas is really, really hot, means it has a really large amount of energy. Okay, so one of the things that happens when you have a lot of energy is that produces a lot of gravity as well. So normally we think of gravity as being, oh, the Earth has a big mass, and so it will gravitationally attract anything to that mass. And the sort of simplest formulas for gravity just say the gravity is proportional to the mass of the object that is the two masses of the objects multiplied together. But in fact, there's an equivalence between mass and energy, and gravity is also produced by energy as well as by mass. So, famous formula is E equals mc squared. The energy is equal to the total energy of something, at least if it's staying still, if it isn't moving around. Total energy is the mass times the speed of light squared. And let's see, we can, that most of the time, so energy, you take an object, you just move it around. It'll have a certain energy associated with motion. That energy is roughly a half times the mass times the velocity squared. That's the standard formula for kinetic energy. But there's also an intrinsic energy associated with the object. And if you were to somehow get rid of the mass in the object, then you could convert that to a certain amount of energy. So for example, a place where that happens is, let's say you have an electron and an anti-electron, a positron, and you let them annihilate each other. They can interact, they can annihilate each other, and they can produce two photons. And so then, in a sense, you're taking the mass. Let's say you just got this electron and the positron, and they're just hanging out near each other. Actually, there's a weird thing called positronium, which is a kind of atom where the nucleus of the atom, the quotes nucleus, is a positron, a positively charged analog of the electron, and then there's an electron sort of going around outside it. Positronium can be stable, but if you just have the electron and the positron sitting there and they just sort of amble towards each other, there's no real velocity involved, but eventually they come sufficiently close that they react and you end up getting two photons out. Okay, so in that case, you're converting the rest energy of the electron and the positron to the pure energy of photons. Photons have zero mass, and so sort of everything that is there is just the energy of a photon, not its rest mass. And so that formula E equals mc squared tells you the energy of those two photons that will be produced by the annihilation of an electron and a positron at rest. But in general, the full formula, if you're into these things, is E squared equals P squared C squared plus M squared C to the fourth. So what that formula says is the energy has a term that depends on the momentum, and it depends on the rest mass. And so the total energy of something depends on sort of how much it's moving around. That's the sort of kinetic piece, and its intrinsic energy associated with the rest mass of the thing. Okay, so as far as gravity is concerned, it doesn't really care very much where the energy is coming from, whether it's coming from rest mass or whether it's coming from momentum. It basically treats those as kind of the same type of thing. It's a little bit different in detail, but basically the same kind of thing. And those are both sources of gravity. And so in the sort of official version of this is Einstein's equations, which represent gravity in terms of the curvature of space-time. And the curvature of space-time is proportional to a thing called the energy momentum tensor, which is sort of a combination of energy and mass and momentum and so on. But in any case, the basic bottom line is energy, like mass, is a source of gravity. Okay, so imagine we have this gas in a box and we heat the gas up really, really high temperature. It's going to have a lot of energy. That energy is going to be a source of gravity. And so what will happen is that as we make the energy sufficiently high, that there will be so much, the energy associated with this gas will be such that it will produce, there'll be a huge amount of gravity associated with the energy of this gas. And eventually it'll get to the point where there's so much gravity that it basically makes the space around the thing kind of implode on itself. So how does that happen? So, and essentially form a black hole. So what happens there? Well, the more gravity there is, let's say there's an object that has a certain mass and it has a certain size, it produces a certain amount of gravity on its surface. And now you ask the question, how difficult is it to escape from that thing? So you fire a rocket up and you're trying to get away from the gravity of that object. How fast do you have to go to escape the gravity of that object? For the Earth, if you go more than 25,000 miles an hour, you will escape from the gravity of the Earth, and you can have a spacecraft that goes at that speed. It'll if you go more than that speed, you can just wander off into the rest of the solar system, or into the rest of the cosmos, so to speak. For the sun, at the surface of the sun, the escape velocity is somewhat bigger. It's 100,000 miles an hour. So that's the speed you have to get to if you're going to escape from the gravitational pull of the sun from the solar system, for example. I think for the whole galaxy, it's about 1 million miles an hour. But in any case, the question is, if you have an object that has enough mass concentrated in a small enough area, small enough volume, the gravity is such that the escape velocity will get larger and larger and larger, and eventually the escape velocity is more than the speed of light. And since you can't get something to go faster than the speed of light, that means nothing can escape from that area, and that's what it means to form an event horizon, which is what defines a black hole. Nothing can escape from that event horizon, because if you tried to sort of fire a rocket out, the fastest you could ever fire a rocket out would be at the speed of light, but even things at the speed of light are pulled back in by the gravity of that object. So if you make something sufficiently hot, you would eventually get to the point where there will be so much gravity produced by the energy of that thing that you will end up forming a black hole. And that's sort of a limit on the temperature that you can reach for things. And well, let's see, there are other limits to temperature. So one of the questions is, what will happen to space-time, for example, if you put more and more energy into space-time, what happens? Well, in our models, we can, let me think about this for a second. Yeah, I think, I think what happens is basically you form little black holes or other much more bizarre features of space-time. You're essentially having it be the case. So roughly the reason this happens is in our models of space from our physics project, which we think really is how physics works, at the smallest scales, space is just made of a giant network of points. We have this idea that space is sort of continuous, we can move around anywhere we want, but in our model of physics, that isn't the way it works. Instead, there's this underlying structure at a very, very small scale, trillions and trillions of meters in size. There's a structure where space is this kind of giant network of points. And what happens is, if you say, well, what's the shortest path from one place in space to another through this kind of network? Well, if in many cases, that shortest path is basically just a pure straight line. But what happens is that energy is associated with the amount of activity in this network. So this network is continually getting rewritten. In fact, that's kind of how space is knitted together. If it wasn't for the fact that the network is locally getting rewritten all over the place, the different parts of space would never communicate with each other. And we wouldn't have something that behaves like space that we can move through and so on. But in any case, it's sort of continually being knitted together. But the rate at which it's being knitted together in any particular region of space is, in our models, determined by the energy at that place in space. So the higher the energy, the faster the rate of kind of rewriting space that is happening. And so that process of rewriting means that if you look at the shortest path from one place to another, it is deflected by all that rewriting that's going on. Essentially, if you were to look at kind of what's the fastest way to get through the network from one place to another, if there's a lot of little pieces of network in there and a lot of sort of density of network, then it's kind of, you tend to want to go through that place where there's more network in some sense. And that's why the sort of the shortest path is deflected. And that's kind of ultimately the explanation for the reason for the force of gravity and the deflection of what are called geodesics, shortest paths in space. So in the case where you have a sufficiently high energy density, all kinds of crazy things will happen with those shortest paths. And I'm not absolutely sure what would happen if you just inject more and more, you just rewrite this network faster and faster and faster. I think what will happen is just that the shortest paths will all get captured into that region where everything's getting rewritten. It's like all the action in the universe is going on just in this one place. And so kind of all paths that you follow will just get dragged to that place in the universe. And that's sort of what will happen as you try and make the temperature incredibly high to put an incredibly large amount of energy there. Now, the actual value of the temperature you need is some ridiculous trillions and trillions and trillions of degrees centigrade to achieve anything like that. But that's, I think, the final thing that happens. Now, there is one funny thing. In the very early universe, temperatures, well, were effectively a lot higher. Maybe I shouldn't explain that. That's a different story, perhaps. There's maybe one other thing to mention about temperature. So when you heat things up, you're effectively, as things are going faster and faster. Boy, is this going to be easy to explain? I'm going to try and tell you about why people thought at one time there might be a maximum temperature, and not associated with this effect about gravity and making black holes and things like that, but a quite different kind of maximum temperature. And yeah, so the idea is this. Normally you say, well, I've got a bunch of molecules and they're bouncing around and we're making it hotter. Eventually, those molecules, things will get so hot that the energy that's binding the electrons in those binding the atoms and the molecules together, the electrons to the nuclei of the atoms, you'll have so much energy associated with things bouncing around and colliding with each other and so on, that you will no longer be able to keep the electrons bound to nuclei of atoms, and the things will get torn apart into a plasma. That's what fire is a plasma where the nuclei of atoms have been separated from their electrons. So that's the first thing that happens. Now, the question is, you might think when things are sufficiently hot, oh, it's just a bunch of nuclei bouncing around. But here's a weird thing that can happen. Let's say that that there are various ways to make new kinds of particles. Let's say that you have, so when you heat things up, normally you go from ordinary matter to plasmas, and if you heat things up even further, so in a plasma, you've torn the electrons away from the nuclei of atoms. So if you go to even higher temperatures, you will start tearing the nuclei of atoms apart. And in particular, you can kind of tear apart the pieces of protons and neutrons. And so what happens is you get what's called a quark gluon plasma. What's inside protons and neutrons are quarks and these gluons, which are particles that get exchanged between quarks, that kind of pull the quarks together to sort of bind them into a proton or something. So at sufficiently high temperatures, you get this kind of quark gluon plasma. That's the current belief about what happens, and that's been observed in some particle accelerators, at least to some extent. You get very, very small amounts of quark gluon plasma for very short amounts of time. You can kind of tell that it's this kind of blob of stuff at a very high temperature. Okay, so that's what people think happens. Now, but nevertheless, you've gone up to this very high temperature. Everything is turned into a bunch of quarks and gluons. But the question is, what would happen? But you have this high temperature, and the energy associated with the temperature is just going into the kinetic energy of the particles. It's just making these particles. Maybe it tears apart the atoms. Maybe it tears apart the protons. But it's still basically the energy that you keep on putting in just goes into making particles run around faster and faster. Okay, there's one weird thing that could happen. What if there are more kinds of particles that you could produce? And what if, as you put more energy into the system, instead of that energy going to particles running around, it goes into making new kinds of particles that have higher masses? So I said that the mass and energy have this equivalence. That's what E equals mc squared is telling you. That tells you that you could take like that positron and the electron, and they could annihilate each other, produce sort of pure energy, at least the photons that don't have a rest mass. You can also go the other way around. You could take those photons that are just sort of energy, no rest mass, and have them interact and produce an electron and a positron that have a mass. So just as you can go from mass to energy, so you can go from energy to mass. And so as you pump more energy into this system that is at an increasingly high temperature, you might think that all that energy you pump it in is making just the particles run around faster and faster. But there's another possibility, which is if there are more kinds of particles you can make, you might just be making new kinds of particles rather than having that energy go into your existing particles running around faster and faster. And there was a model back in the 1960s when people had different views about how particle physics works. There was a model which said that the number of kinds of particles should increase exponentially with their mass. So in other words, as right now we know about some number of kinds of particles, but there will be more and more and more and more particles. And as you increase the mass, the numbers of types of particles that you would just get incredibly much larger. So, I mean, in fact, that theory was somewhat related to string theory, which has been kind of a popular mathematical development in mathematical physics in the last particularly 30 years. It's sort of related to that. The buzzword for this is the Hagedorn temperature. But the idea was that instead of energy going into making particles go around faster and faster, the energy would go into making more particles. And what could happen is if you have an exponentially increasing number of kinds of particles, you eventually will get to the point where the more that you try and put more energy in, and all you'll get is more particles, more new kinds of particles produced, not something which is sort of traditional temperature with kinetic energy. So that's a different form of maximum temperature that doesn't seem to be the way that it actually works. Let's see. The question from Wobbin here, is void space really void, or is there something there? There's no notion, I believe, of space unless, in a sense, there's something there. So in our model of physics, for example, space is made of this giant network of points. And in order for us to, for example, move through space, in order for a spacecraft to go through space, there kind of has to already be some network of points there. Otherwise, as the spacecraft itself is just a feature of space. It's like when you have water, for example, you've got all these molecules bouncing around and they make up the water, and then you can have a vortex. You run your finger through the water, you'll see this little whirlpool going behind your finger. That vortex can move through the water, even though that vortex is ultimately just made of a certain configuration of the underlying molecules, but that an electron or a spacecraft, for that matter, going through physical space, it's kind of the same sort of story. There's an underlying structure of space that's like the way that the molecules make up the structure of water, and then there are features of that we notice, like electrons or spacecraft or whatever, that are like the vortices in the water. So in order for the vortex to be able to go through water, there's got to be water there that the vortex is going to be made of. And so it is with space. that there's no way to kind of expect to move around in space unless there's already space there for you to move into, so to speak. So you're kind of like the vortex operating, on this background. There's all these little points in space all connected together in this network, and the network is continuously changing and so on. So space, empty space, is actually an incredibly active place. If you were to look at it at a very small scale, not that you could look at it in the ordinary sense of looking, but if you were to at least kind of conceptually imagine what's going on there, it's a place of incredible activity at a small scale. Just like in the water, there's incredible activity of all these molecules bouncing around, even though all you see is that vortex going across the surface of the water. And so if it wasn't for all that activity in space, space would not be knitted together. There wouldn't be any way to move from one part of space to another. There wouldn't be anything to move into. There wouldn't be anything to sort of for you to be when you move to that other part of space. And actually, one of the things that's a little bit sobering is it looks like the fraction of the activity that's associated with all the things we care about, electrons and spacecraft and all that kind of thing, is just 1 part in a trillion, maybe, or more, of the actual activity in space. So the vast majority of what's going on throughout the universe is simply the knitting together of the structure of space. And we're just a little piece of kind of froth on top of that is everything that we care about. So that's in our new models of physics, that's kind of how we think about it. It's been known actually for nearly 100 years that there is activity in space. I think it's much clearer now what that activity is, and that activity is actually necessary to create the structure of space. But it's been known that there's sort of stuff going on even in a vacuum in empty space. That's been known for 100 years. It's been known ever since people started figuring out about quantum mechanics. And what's been believed is that there are so-called vacuum fluctuations that at all times there are always virtual particles being produced and being created and annihilating all the time, everywhere in the vacuum. And in the end, that claim is probably equivalent to the way that our underlying models work for space, although I think our underlying models for space are in the end, much deeper models, but you don't get quite up to the froth that we care about with the electrons that we actually see and that move around and so on. But the kind of traditional quantum mechanics is at a layer just below that. Then there's this giant ocean of stuff, which is what our models talk about, that's below that, the really low-level kind of machine code of the universe that's below that. But if you go almost up to the surface of things that we care about, you get kind of the traditional ideas of quantum mechanics, of which the most, the one I'm mentioning here is vacuum fluctuations. So what happens is that let's see, the sort of standard description of this is in a vacuum, there are virtual pairs of particles and antiparticles that are continually being created and destroyed. What that means is in standard physics, there are properties that something like an electron has. It has a certain mass, let's say. And because of the mass, it has a certain relationship. You can compute its energy, you can compute its momentum based on it moving around. And there's a certain relationship between energy and momentum that's determined by its mass. In fact, that formula I was telling you before, E squared equals P squared C squared plus M squared C to the fourth, that is the relationship between energy, momentum, and mass. And for an ordinary electron, they just pick up, you don't really pick up electrons because they're too small, but an ordinary thing, a particle that exists and that can move and go around the universe, it has a certain relationship between energy, momentum, and mass. Okay, but it turns out that according to quantum mechanics, particles can exist that do not have that relationship. They are what's called they're off their mass shells. That's a bit of a weird mathematical statement, and You think about you can think about these things in terms of vectors, and you can think about the length of the vector. It's a 4 vector. The length of the 4 vector, the square, is determined by the mass, and that's why when you say if the length of a vector is a constant, then that corresponds to the vector sort of tracing out the surface of a sphere, and that's why this phrase "on its mass shell" comes up. So when an electron has its ordinary relationship between energy and momentum, it's said to be on its mass shell, and it's just an electron that can go around wherever it wants. But according to quantum mechanics, for a very short time, an electron can exist that does not have the ordinary relationship between energy, momentum, and mass. It can be off its mass shell. In fact, it can have pretty much any energy and any momentum, but the amount that the time it can exist for gets shorter and shorter the further away it is from having the usual energy, momentum, mass relationship. And that idea of particles that don't quite have the usual relationship, that's the idea of virtual particles. So a place where virtual particles are important is, let's say you have an electron, 2 electrons, and they are just going along. An electron can emit a photon, and that photon can travel to the other electron, and that photon has momentum. So the photon can essentially give a kick from one electron to the other, and that's so it can transmit a force from one electron to the other. But that photon doesn't exist very long. It's emitted from one electron and it's absorbed moments later by the other electron. And because it doesn't exist for very long, it doesn't have to be a real photon. It can be a virtual photon that has a weird relationship between energy momentum, and in the case of photons, 0 mass. It can act like a photon that doesn't have 0 mass. It can act like a photon that has some huge mass. And it can do that according to quantum mechanics, but only for a very short time. And the larger the effective mass, the shorter the time that it can exist for. So it's kind of like quantum mechanics says you can make a mistake about the mass, but not for very long. Eventually your mistake will catch up with you. And so let's see, so there's this idea of virtual particles, and that you can have things which completely kind of mess up these energy, momentum, mass relationships, but only for a very short time. So in particular, they can mess it up to the point where you can have an electron and a positron created out of empty space, and they can exist, but only for a short time. You can create that mass, but only for a very short time. You can create the mass of an electron and a positron, and so you're kind of violating the usual principles about how that should work, but you can do it, but for a very short time. So everywhere in the vacuum, there are little virtual particle-antiparticle pairs being created and then destroyed. And there are sort of ones of higher energy that last for even shorter times. There are ones of lower energy that last for longer times, but that's happening all over the vacuum. And it's supposed to be vacuum, but it's actually got all these fluctuations going on. Now, those fluctuations are a kind of junior version of the story that I'm telling about the sort of rewriting of space. The rewriting of space is a lower level, a much more intense process than this particle-antiparticle thing. Essentially what's happening is the particles are like little things like vortices on the water. They're like little features of space. And so what one's saying in quantum field theory, which is the kind of theory that talks about virtual particles, in quantum field theory, what one's saying is that there's continually activity going on in the quantum fields have this activity. That is kind of a shadow of this much deeper activity that's going on in the structure of space, according to our models. In any case, in quantum field theory, there are these virtual particles that exist everywhere in space. The significance of them is not much at all in quantum field theory. It's just they're a thing that's there. In our models that go deep below quantum field theory, those virtual particle phenomena are incredibly significant because they're the things that make space possible. They're the things that create the structure of space. But in traditional quantum theory, they're just things that happen to be there. The uncertainty principle, which is a general principle in quantum mechanics about how precise you can make things, basically says that nothing can be made absolutely precise in quantum mechanics, including counting how many particles you have. There's always some error in that, and that's why there will be virtual particles. That's one explanation of it. Anyway, bottom line is there are virtual particles in the vacuum everywhere. Okay, one question is, can you tell? One embarrassment is there are so many virtual particles that in the very traditional version of quantum field theory, the one that people have sort of believed in for the last 100 years, there are so many of these virtual particles, they would create lots of sort of bubbling energy in the universe. And that energy would be enough to create a huge amount of gravity, which would curl the universe up into a tiny ball. And so one of the things that has been a mystery is why vacuum energy, as it's called, does not basically destroy the universe. And in our models, we kind of understand why that is. It's because that thing that one's describing as vacuum energy is actually what makes the universe. It's actually what makes the structure of space. And so it's not that you are just handed all this activity in space that already exists, which would cause that space to kind of curl up in a tiny ball. It's that that activity makes the structure of space. Okay, but in traditional quantum field theory, what is the effect of all these fluctuations in the vacuum? Well, there are all kinds of effects, and people have measured some of those effects. Probably the most famous is a thing called the Casimir effect. And here's how it works. It's kind of a weird thing. You take two metal plates completely in the vacuum. Two metal plates, they don't have any electric charge, nothing like that. Two big metal plates. You put them in the vacuum, and there's a small force of attraction between them. Very weird. So what is that caused by? What it's caused by is that there are vacuum fluctuations that are happening between the metal plates. There are vacuum fluctuations that happen outside of the metal plates. But the presence of the metal plates basically restricts the kinds of vacuum fluctuations that can occur between them. Roughly what happens is that when there are these virtual particle-antiparticle pairs produced, roughly the lower the energy, the bigger the virtual particle-antiparticle pair ends up being, sort of the greater the extent. And the ones that have very low energy they just don't fit between these two metal plates if you have a certain distance apart. So some of the low energy vacuum fluctuations don't occur in between the metal plates, but they do occur outside the metal plates. So that means there's all those high frequency, high energy fluctuations happening within the metal plates. They're also happening outside, but there are some low energy ones that are missing between the plates, but still exist outside. So what does that do? That means that there's a pressure pushing the plates together because those fluctuations on the outside are there, they're not there on the inside. So there's this imbalance and the plates get pushed together. So that effect is a small effect, but it's observed. Now, turns out you might have thought, or people thought for a while in the 1930s, people thought that maybe electrons were held together by this Casimir force. But it turns out when you work out the Casimir force for a spherical object, bizarrely, instead of it being an attractive force, it's a repulsive force. And it just kind of tells you that the math is a little bit more complicated than what I was just telling you. That's just a way of thinking about it that works out well in that case. There's another effect, so it's called van der Waals forces or London dispersion forces. Those are forces that are very important in chemistry, that are forces that hold that the force of attraction between neutral atoms. So if you just have two atoms in just hanging out and they don't have any electric charge on them, there's still a force of attraction between them, and it's associated with something to do with vacuum fluctuations. It's a little complicated. What happens is there are vacuum fluctuations that kind of elongate one of the atoms and cause it to have an electric dipole moment. They cause it to separate its positive and negative charges. And that separation of positive and negative charges induces a separation of positive and negative charges on the other atom. And then those two sort of separated positive and negative charges have a little force of attraction between them. And that's a very important thing in kind of in holding materials together, the so-called van der Waals forces. And they are ultimately can be thought of as being the result of vacuum fluctuations kind of causing that sort of temporary sort of separation of charge in atoms. So that's a little bit of a story of what's in the vacuum. Lots of stuff. The vacuum in some sense has everything in it, just bubbling around. And we are simply seeing, when we see material objects and particles and things like that, we are seeing kind of the just particular features of what exists in, at least in a virtual way, everywhere in the vacuum. Let's see. Well, there are okay, there's a question about space. Does that mean there are more dimensions of space than we usually think of? Yes, the answer is yes. In these models of space where everything is just a network connecting points together, there's no reason for that connectivity to lead to something that is like 3 dimensions. Like you're moving around in this network, you can go anywhere on any one of the network connections. And it could be the case that on average, you will have just 3 different directions in the network. But that doesn't have to be that way. And certainly on a sufficiently small scale, it will not be that way. You will not see that the 3 dimensions is sort of this emergent thing on a large scale. On a small scale, it won't look like that. And when the universe was young, you know, shortly after the beginning of the universe, when the universe was small and the Big Bang, when the universe started expanding, I think it's very likely that the universe was infinite dimensional, that the universe was a network that's very, very, very connected. So you can go in any direction. There are an infinite number of directions you can go in, infinite number of separate directions. And then gradually, as the universe kind of expanded and cooled down, then it got to the point where space only had, on large scale, 3 dimensions. But on a small scale, there isn't really even a definition of dimension, but you can think of it as being sometimes even sort of much higher dimensional than space normally is, maybe lower dimensional as well. There isn't really a definition until you get to sort of a large scale. It's just like if you say, what's the density of water? You say, well, on a large scale, there are this number of molecules in this volume of water. But if you go down to a small enough scale, you'll be looking at these tiny little areas and you say, oh, a molecule just went by, or another molecule went by. And you won't be able to say, you'll say, well, the mass divided by volume, which is what density is, the amount of mass in this volume, right now it's a whole 3 water molecules. Oh, at the next moment it's 7 water molecules. It keeps on fluctuating around. And it's the same thing with dimension when you look at these networks and so on. Well, let's see. I have to go fairly soon here. Let me see if there's something that I can try to answer here. There's a question from Aaron that I don't know the answer to. It's asking, from how many discrete stars was our Earth made? Our Earth is the fact that we have heavy elements like gold, anything beyond iron in the periodic table, is a sign that our star, our sun, our solar system was not a first generation thing in the universe. At the beginning, really all one will have is hydrogen, and the production of heavier elements is the thing that has to happen in things like supernovas, star explosions, and that's so we know we're not first generation, so to speak. We know we're not freshly made from the stuff that the universe originally started from. But exactly how many, it's a very interesting question, actually. I don't know the answer to that. How many distinct stars sort of were sort of pulled together to make the sort of primordial cloud of stuff from which our solar system condensed? And I wonder if there's any way to tell. The only way I can imagine is the relative abundance of various isotopes. different variants of elements, where there are different numbers of neutrons in the nuclei? I don't know. I don't know the answer to that. It's an interesting question. Prutz is asking, can we tap the Casimir effect for energy? Okay, I'll tell you a funny story here. So back in 1981, I wrote a paper with a friend of mine named Jan Ambjorn about Casimir energy. It was a paper called Properties of the Vacuum, Part 1, Mechanical Properties. We had a Part 2, which was electrodynamic properties. We'd advertised a Part 3 about gravitational properties, which we never wrote. And Jan, because he was had an alphabetically earlier name than mine, just kept on getting requests over all these years, for 40 years, getting requests, where's Part 3 of this set of papers? And I realized with our physics project now, we could actually write, I actually know how to write a Part 3. I think I'm still working on Jan to understand what we're doing enough to be up for making a Part 3 of this thing. Jan himself has worked on actually the discrete models of space-time of a slightly different kind that I think are equivalent to ours, but it's a complicated story. But anyway, okay, so we wrote this paper about mechanical properties of the vacuum and looked at this Casimir energy phenomenon for different kinds of quantum fields and different configurations. And we looked at particularly boxes that are like cuboidal boxes, okay? And you put a field, a quantum field, in those boxes, and you say, is the force on the walls of that box, is it attractive or repulsive? And depending on the shape of the box, the force law, the forces are somewhat different. And as you change the shape of the box, the forces change in this very strange way. And so we had this picture that I made with a computer calculation back in 1981 of the forces as a function of the shape of the box. Okay, so a few years go by, and a physicist and science fiction writer named Robert Forward looks at this picture. He says, wait a minute, I can take that picture and I can make a closed cycle where I take this box and I change its shape to this, to that. I can make a closed cycle of sort of shapes of the box, just like you would have in a car engine or something. You would have a closed cycle of, you open the cylinder up, you fire something, you push the cylinder down. It's a cycle. That's a very typical thing to look at in machinery, is some kind of cycle. So you can imagine the cycle of a box that's just sitting there in the vacuum. Okay, so what he noticed was that based on our calculations, if you went through this closed cycle, you could actually extract energy from the vacuum. So he wrote to me and said, is the calculation really right? I think so, according to, it's a long time ago, but according to the physics that we know, this calculation is right. Although there are some approximations that you're using for representing this box, which are kind of questionable. Anyway, so then the conclusion from that is, well, you could extract energy from the vacuum. And so this idea of zero-point energy and zero-point energy as a method for example, propelling spacecraft and so on, that became a thing that was discussed in a bunch of NASA workshops, et cetera, et cetera, et cetera. And people tried to measure the effects and the size of the effects and so on. But the thing to me, whatever its life in science fiction has been excellent. And I'm always kind of amused when in some movie or something, there'll be some device that is said to work using zero-point energy, because that came out of that work that we did on the Casimir effect and zero-point energy. Now, does it actually work? No, it does not actually work. And the reason it doesn't actually work is that to make it work, you have to have a box that can kind of contain every possible thing that a quantum field does. And the problem is that you make a box out of metal, for example, it has atoms, the atoms are a certain distance apart, the atoms have a certain energy binding them together, et cetera, et cetera, et cetera. It can kind of constrain, it can keep inside, contain a certain range of things the quantum fields can do, but not all of them. There will always be sort of very high frequency, very little jitters in the quantum field that will always get through between, you've got a metal box, you've got atoms of the metal, they're a certain distance apart, maybe a tenth of a billionth of a meter or something apart. But nevertheless, there will be a little jitter in the quantum field that's even smaller than that, so it can get through. So there's no material you can make the box out of that will cause it to be able to contain the quantum field in the way that you would need in order to be able to do this closed cycle of extracting energy from the quantum field. Now, as I'm talking to you about this, and I'm thinking about part 3 of our series of papers, which we never wrote, and I haven't written an academic paper since 1986. I've published what I do in different ways. But in any case, I think as I'm thinking about it, the one interesting case where you could expect to make things like this work is if the walls of the box, in a sense, are the event horizons of black holes. So if you could make something where you contain the quantum field inside essentially a black hole, and you're distorting the shape of the black hole, then that will be a different story. Now, you know, at the first level, that's kind of a loser of a story, because yes, you can squidge around the black hole, maybe, and you can have the vacuum energy inside it change, but it's like, it's inside a black hole. What are you going to do with it? You know, you could say, I've got a lot of energy in there, but it's inside a black hole and I can't get my hands on it. But it's a little bit more complicated than that, I think. And I have a suspicion that there is, at least in principle, there might be a way, that's an interesting thought, there might in principle be a way of mining energy from the vacuum. How do you get, you know, what does it mean to mine energy from vacuum? What would that mean? It would mean that you're gradually taking some of the activity of the network that knits together the structure of space, and you're turning that energy that's just knitting together the structure of space into organized energy that can, for example, correspond to the motion of electrons or the motion of atoms or something. So it's very much like what you have to do. So one of the things about, it's sort of a fundamental result about thermodynamics, which comes in many forms, but one form of it is heat does not flow, heat flows from hotter bodies to colder ones. In other words, you have all these molecules bouncing around in a hotter body. They can make molecules in a colder body bounce around more by transferring some of their energy, but the colder body can't somehow make it, you don't sort of transfer heat. The colder body doesn't get colder and transfer its heat to the hotter body. And another version of that is to say, it's difficult to take heat and make it into mechanical work. And why is that? Well, it's because the molecules are all bouncing around randomly. But mechanical work, like moving a piston, is about taking a bunch of molecules in the piston and having them all move together. It's kind of a way and so the question is, to what extent can you get all these molecules that are randomly bouncing around to do something that is systematic and move the piston in a systematic way? And it's the difficulty of doing that is the difficulty of extracting sort of energy from heat, extracting useful work from heat. And that's kind of when you make a steam engine or something, that's the big thing that you achieve, is to take heat and extract mechanical work from it. So I think what one's asking for here in extracting energy from the vacuum is the same type of thing. Can you take the heat of the vacuum, so to speak, all this random motion, not motion really, all this random rewriting of the vacuum, rewriting of the structure of space, can you take that and can you organize it into actual things that we can recognize as particles going around with certain energies, velocities, whatever else? So that's really the question. It's really the extraction of useful work from the vacuum, I think, is very much the same kind of thing as the extraction of useful work from a sort of random gas with a certain temperature. So the question then is, how would you go about, how would you make the analog of a heat engine? So that's the name for the type of thing that a heat engine is, something which just takes heat and turns it into mechanical work. So the question is, what is the analog of a heat engine in the case of space-time? And is there a heat engine that can take the vacuum fluctuations in the universe and turn them into useful mechanical work? That's an interesting question. I've not thought about it that way before. My guess is that there is such a thing, and that you can, at least in principle, imagine constructing it using, well, things like black holes. And it's an interesting question how that would work. It's a good thing to work out. Actually, I think this analogy, which I hadn't really considered before telling you guys about it right now, about sort of the idea of what it takes to go from sort of the random structure of space to something systematic. That's kind of a that gives a very close analogy between well, what's the second law of thermodynamics, a phenomenon I call computational irreducibility, and these questions about extracting energy from a vacuum. That's an interesting thing. So that's a piece of technology. If there's a way to do it, I think it's a few hundred years in the future. But and sometimes it's kind of a terrible thing, because you can realize that there's basic science that allows you to see how something's possible, and then you realize we are so far away technologically from being able to do this. I mean, the great example of this is when Isaac Newton figured out about laws of motion in like 1687. It's like from that point, one could have known, and I think he knew, that you could in principle have a satellite that would orbit the Earth. But it took until 1957 until that was actually put into practice. So sort of almost a 300-year span. So it's one of these things where it's a little bit funny to be able to see these things which are in principle possible, but then it's so far in the future to actually be able to achieve them. And some things maybe even further, because it may require, it may require energies and so on, which just are far away. I mean, to make a rocket requires kinds of things that will make a rocket that will reach orbit, requires kind of a way of making sort of explosive energy that certainly did not exist in Isaac Newton's time. I mean, I guess fireworks existed, but it's a bit of a far cry from a firework to a satellite launch. But it took a while to have that happen. Parker is asking, constraining vacuum fluctuations using some sort of field. Yeah, the problem is that a field has the same features. So sometimes, for example, in constraining a plasma to sort of squash it down to be able to achieve nuclear fusion, you can use magnetism, you can use a magnetic field to do that. It doesn't have the same problem of sort of just having atoms and things escape from the atoms. But what will happen is for this case of dealing with vacuum fluctuations, the problem is the field that you use to constrain it will also have this difficulty that it has only certain essentially frequencies of activity in it, and there'll always be pieces that can escape. With the possible exception of an event horizon in gravity, which is a little bit of a different situation. And that's a possible case where you could do this constraint. And that's in a sense a field. It's a gravitational field, but it's a gravitational field that has very weird properties about essentially, well, maybe you could do it another way too. Yeah, okay, so with an electromagnetic field, electricity and magnetism, that electric and magnetic fields don't hold themselves together. You can make an electric and magnetic field, you can put it somewhere, you can produce it in some region of space, but the field itself does not affect that field. The field itself, an electron can affect the field, but the field doesn't affect the field. For gravity, that's not true. Gravity affects the gravitational field. So because the gravitational field itself effectively has an energy, and that energy has an effect on gravity, the gravitational field affects the gravitational field. It's a nonlinear process where gravity affects gravity. And that's what allows you to get things like black holes, where the intensity of gravity affects the intensity of gravity. There's another case we know where that happens, which is in the gluon field that holds the quarks inside things like protons. That's another case where there is this nonlinear effect where the field affects the field. And so I am wondering, although it's, oh, that's pretty funky actually. I am wondering whether there's a possible way to use quark-gluon plasmas and to use that nonlinear field to make some kind of sort of constraining bottle. But I don't think that would work, because I think that the problem is that anytime you have a size of field that is constrained by a certain sort of size that you understand, that size will never be able to catch all the little jiggles of the vacuum fluctuations that are of all possible sizes. So I don't think that can work, but will be an interesting thing to analyze properly. All right, lots of interesting physics today. I have to go. As a matter of fact, for those interested, I'm going back to my day job here, and we've got a live stream doing a design review of some Wolfram language features. I do want to make the plug that for people who actually want to sort of dive deeper and understand how to do science and discover things in science and so on, use Wolfram language. It is the thing I just spent the last 40 years building to make it possible to discover things in science. And I have lots of fun discovering things in science. So do lots of other people with it, and it's a really good thing to learn for the purpose of understanding science and exploring science. And even if you're at a pretty early stage, you've got a tool set that is very powerful and lets you kind of jump ahead and discover things that people have never had a chance to discover before. And I'll make a final plug for the Elementary Introduction to Wolfram Language, which is a book that I wrote, which you'll find free on the web, and good thing to start with if you haven't already done so. All right, we should wrap up here. Thanks for joining me, and see you another time.